Welcome to the lesson on 10.3 for CTM about modular arithmetic. So here's some new vocabulary to know for this lesson. Make sure you're using those extra examples in your book. Going to do quite a few here with you, and there's a lot more in the book to help you out as well. So let's get started with 10.3. Let's define a couple of things first. Actually, three things first. So let's put that stuff up here. And let's start off by defining what a modulo M system is. So a modulo M system and we're also going to define modulus within the context of this sentence. So where M is the modulus of the system. So what this modulo M system is it's something that consists of M elements, and those elements are 0 through M minus 1, and it also has a binary operation. So and a binary operation. Remember, binary operations are just things you do on two elements of the system, and they give you one. They basically spit out a single element. You do the binary operation to the two elements, and it gives you another element within the system. So very, very similar to what we did with adding, subtracting, multiplying, dividing in different bases when we had that chapter. So we had the digits in base 7, for instance. You have the digits 0 through 6. Same thing with a modulus. If you have modulus 7, a modulo 7 system, you would have the digits 0 through 6. It consists of those elements now instead of those digits in bases. So very, very similar to what we had with bases before. And a number A, so the number A is congruent. So some number, any old number, is congruent to B modulo M and if you write that out, it's written A, and then this symbol means for modular arithmetic, this means is congruent to. So A is congruent to B mod M if A and B have the same remainder. When divided by M. And so there will be some instances where I want you to use a different color with this. This is one of those instances right here. So this right here, if you're reading this out loud, this means you would say is congruent to. So if you're reading that, that's what that looks like. That would be is congruent to. And so back to our normal color here. Let's just do a quick example to show you what all this means. So let's say I had 10, and I wanted to write 10 in modulo 7. So I would have to divide 10 by 7 and see what I get. That would be 1 with a remainder of 3. And so this implies that 10 is congruent to 3 mod 7. Because 3 is the remainder, that means 10 is the same thing as 3 in modulo 7. So let's do a couple more quick ones here. 3 divided by 7. If I want to write what's 3 congruent to in mod 7, basically leaving this spot blank. It's essentially how I was thinking of it before. So this is the grunt work, you might say, to get to that answer. So 3 divided by 7 is 0 with a remainder of 3. Basically what we're doing here is we're dropping off the actual quotient, and we're just taking the remainder. So 3 is the same thing as 3 mod 7. And let's try one more here. 31. What is 31? Well, it goes into 7, or 7 goes into 31 4 whole times with a remainder of 3. So this 31 ends up being congruent to the same thing, 3 mod 7. So this is an example where they all worked out the same way. And I did that on purpose. Do they always turn out to be the same thing? Definitely not. So this one is just an example, a quick example of 3 numbers that end up being congruent to exactly the same number in modulus 7, because they all have the same remainder. So let's check out, I think, a pretty important thing here. These are some everyday examples of modular arithmetic. So this is actually very practical, very useful, what we're doing here. You actually use modular arithmetic every day without really thinking about it, I bet. So everyday examples of modular arithmetic. Let's just write these things down here. So seconds in, thinking of writing in and an at the same time. Seconds in an hour, not an hour. Not yet. We could do that too, I suppose, but in a minute is what I meant to write. So seconds in a minute. This would be mod 60, because there's 60 seconds in a minute. So if you had 92 seconds, that would be 1 with a remainder of 32. So you're thinking of it like that. So minutes in an hour. That's another example of kind of modular arithmetic here. That's also in mod 60, because there's 60 minutes in an hour. You could think of hours on a clock. On a typical clock, it has 12 hours, so hours on a clock would be mod 12. So we did clock arithmetic in the previous lesson. If we just replaced this 12 with a 0, you don't have to write down the picture or draw the picture. This now would be a modular arithmetic clock instead of a clock arithmetic clock. So hours on a clock, we can also think of hours in a day. And I think it would be nice if we all did military time instead, because then we wouldn't have to figure out if it's AM or PM. So those that use military time, they're thinking in terms of mod 24 instead of mod 12. You could also think of days in a week. That would be how many days are in a week. That's 7, so that would be, in a sense, mod 7. You could think of days in a year. We're talking a normal year, not a leap year, so days in a year would be mod 365. You could think of months in a year. There are 12 months in the year, so this would be mod 12. Another example I thought of was right here, cents in a dollar. There's 100 cents in a dollar, so this could be considered mod 100. And then you could even think of a car odometer here. So an odometer this is the speedometer part, but this right here, this is the odometer part. So it's telling you how many miles your car has gone. But after it gets to 99,999.9, it's going to roll back over and start over again at 0. So this particular car odometer would be mod 100,000. Some are mod 1 million instead, so I'll write down both numbers. So mod 100,000 or mod 1 million. You might see a car that looks like that instead. And so let's check out some more examples now at this point though. So for this example, we're going to create a table with if you looked at our vocabulary, this was the last vocabulary term there that was written in there, modulo classes. So the modulo, I meant to say modulo 5 classes. Get rid of that a second. Modulo 5 classes for the set of whole numbers. Okay, so what would that look like up here? We need the numbers in modulo 5. So that would just be 1, 2, 3, and 4 with the 0 at the beginning. So just like base 5, modulo 5 only has the digits 0 through 4. It's 0 through m minus 1, in other words. In a different color, let's put this off to the side in a different color here. This is the mod 5 values. In other words, these are going to be the remainder values. So think of modulus, think of remainder. And then here, you would have the actual numbers themselves. So 0 through 4, the remainder is still going to be 0 through 4. But if you divide 5 by 5, you're going to get a remainder of 0. You're going to get a remainder of 0. If you divide 6 by 5, you're going to get a remainder of 1. Likewise, 7 will give you a remainder of 2, 8 a remainder of 3, 9 a remainder of 4. And you could continue this pattern, so 10 gives you 0, and I'm just going to keep going with the pattern. So I'm just going to keep filling stuff in. Any multiple of 0 or 5 will always give you a remainder of 0 when divided by 5. And I could keep going and going and going with this forever and ever and ever, but don't really feel like doing that, so I'm going to put a little dot 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 through each one of these. So basically adding 5 each time gets you that same remainder if you're doing modulo 5. You don't have to draw these columns in. The blue lines on your paper probably suffice for the rows, but as long as you keep them straight. I just did that so you can see more what's going on more easily, I guess I could say. So right here, let's make this note though in a different color. Down here, these are the numbers before the mod 5 is applied. So before you divide the number by 5 and figure out what the remainder is from there. So these are all those numbers, and again this continues on and on and on. So let's check out a couple more examples here. One will be a pretty quick one, or they both will be pretty quick. Just need to change the color back. There we go. So for example 3, we are going to do this. We're going to determine which number from 0 to or through, let me write it as that instead, from 0 through 8, the following numbers are congruent to in modulo 9. So you probably expected I was going to use modulo 9 since I'm doing 0 through 8. It's always one less than that final number is one less than the modulus you're talking about. So let's do a couple of kind of sub-examples here, or examples within the example. So let's say we had 65. So which number is this congruent to in modulo 9? We have to figure out what's the remainder, basically, is all we have to really do. So 65 divided by 9 is 7 with a remainder of 2. Therefore, that implies that you would have 65 being congruent to 2 mod 9. And we'll just try one more quick one of those. 1089. Let's say we had that. You probably wouldn't know what that is off the top of your head, so let's use a calculator for that. So 1089 divided by 9 is, it's a whole number, so you have 121 with the remainder of 0. Could you use long division to do this? Definitely. If you wanted to use long division, that'd be totally fine. But if you can just use a calculator, if they're small enough where you can think of it in your head, you might as well do that. So this would be congruent to 0 mod 9, since there's no remainder with 1089. Cool little trick if you've never learned it. You add up the digits of any number. This always works for 3 and 9. You add up all the digits and you see if the sum of the digits is divisible by 3 or 9. If it is, then the number itself is divisible by 3 or 9. So for here, 1 plus 0 plus 8 plus 9 is 18, and 18 is divisible by 9, so I know this big number is divisible by 9. Kind of cool that it always works out, but we won't get into doing more of that at that point. At this point, just a cool little side note there. So example 4, we're going to evaluate each of the following in mod 4. So let's start off with, now we're going to be adding, subtracting, multiplying some things here. So 2 plus 3, what is that in mod 4? We know 2 plus 3 is 5 if we were just doing normal arithmetic, and we know that 5 divided by 4 is 1 with a remainder of 1. So that means I could say, therefore, 2 plus 3 is 1 mod 4. Always looking at that remainder for my answer. So this number is what goes here. 2 plus 3 is 1, I should say is congruent to, sorry about that. So make sure you're always using that congruent to sign and not an equal sign when you're talking about things in the modulus. So 2 plus 3 is congruent to 1 mod 4. Do a couple of quick more examples like that. 3 minus 1. What would that be in mod 4? 3 minus 1 would be 2, and 2 divided by 4 is the same thing as 0 with a remainder of 2. So this one, that doesn't really make a difference. This is what we are looking for. The remainder is 2. So 3 minus 1 is congruent to 2 mod 4. And we'll do one more here, multiplication on this one. Let's say we had 6 times 3. We know this is 18, and we know that 18 divided by 4 is the same thing as, well, we would have 4 with a remainder of 2. 4 times 4 is 16 with a remainder of 2 left over. Therefore, 6 times 3 is congruent to 2 mod 4. Always looking at that remainder number. Alright, so let's continue with example 5 here. Write this down as your instructions. Find the replacement for the question mark. You'll see it worded like this in your book, so I'm going to word it like this here too. Find the replacement for the question mark that makes each of the following true. And I want you to assume that the question mark is a number less than modular number. Okay, so let's do this first. So 2 minus 6 is congruent to what number? Question mark mod 8. So 2 minus 6, we think of that as being -4, but let's say a negative number is something in mod 8, taking the remainder of a negative number divided by 8. Kind of a little weird to think of something like that. So what can we do instead? Well, we can always take something and add whatever this mod is. If we add 8 to that in this case, since the modulus is 8, that's not going to change the remainder at all. If you take any multiple of 8 and add it to what's here, it's not going to change the remainder at all either. So I would say this looks like a good idea. 2 plus 8 minus 6 would be the same thing as 2 minus 6 in mod 8. Again, that will not change the remainder at all. So this is the same thing as saying this. And then in your different color, let's write down what I just said there. So right here, this is true adding or subtracting. Eight in this case, or any multiple of 8. Usually we'll just stick with the number itself that's right there in the mod. So any multiple of 8 to anything in modulo 8 is allowed, since it won't change the remainder. So we'll have more problems like that, but this is the only time I'll write this actual note, and we'll just see how it applies to different modulus, different moduli. I don't know if that's the plural of modulus, but different modulos, I guess I could say. So what does this become? This is the same thing as 14 minus 6, which is congruent to something. I shouldn't say 14. What am I saying? I'm thinking of a different example here. 10 minus 6. I think I was thinking of 10 minus 6 being 4 mod 8. So I'm getting there. I'm almost there. Let me just use or put that in my next step though. So put question mark still here, mod 8. So this is the same thing as 4 is congruent to, that's going to be 4 mod 8. Because 4 divided by 8 is the same thing as 0 with a remainder of 4, so 4 is what that is. So therefore, you could say that the question mark equals 4. And if you wanted to, you could also say that 2 minus 6, you could plug in the question mark back up there. Here, so the question mark is 4. So 4 mod 8. Alright, so let's check out a second example similar to that, but a little twist here. So now the question mark's not here anymore, it's going to be right here instead. Something minus 12 is congruent to 3 mod 13 now. So can you think of a number that could go in here that would work? Well, if you said 15, I'd say okay, but the number has to be a number, the question mark has to be a number that's less than the modular number. So you could start off by saying that, but this is not less than the modular number. However, the modular number is 13, so remember, just like before, you can add or subtract 8 or any multiple of 8 if it's mod 8. Now we can add or subtract 13 or any multiple of 13 if it's mod 13. So this I could replace with this, 15 minus 13 now, because I want to get this number, this question mark number, to be something between 0 and 12, one less than the modulus. So this would be 3 mod 13 still, and so this would become 2 minus 12 is congruent to 3 mod 13. So we've got our answer at that point. We can say therefore the question mark is equal to 2, and you can say that 2 minus 12 is congruent to 3 mod 13. And just wanted to do one more just like that. So let's call this part C. Just continue this underneath example 5 on yours though. So it goes directly there. Let's say we had 5 minus question mark is congruent to 2 mod 11 now. So modulus 11, what does that look like? And so you could say, well, not exactly sure what this is going to be. It's going to give me a negative number. It's So I'm trying to get something like that right now. But I know that in terms of modulus 11, if I had this number here being, I'm sorry, I gotta erase something here, so I want to erase this. This is why I was getting a little confused sounding. I wanted to make that a 7 and not a 2, because that would have been really easy actually. I could have just said that this was 5 minus 3, and I don't think we really need to see an example like that. I want to do one that's not quite as self-evident right there. So what can this become? So in the same way, so I wouldn't just say 5 minus some number, some positive number, because that's not going to equal 7. So I need to change this, do something similar as to what I did here and to what I did here. I'm going to be now, instead of subtracting like I did here, I want to go back to the thought of adding something to this number. So this is modulus 11. If I took 5 plus 11 minus some sort of question mark, this won't change the remainder at all because it's in modulus 11. So adding 11 to something still gives me the same remainder. This will be 16 minus a question mark is congruent to 7 mod 11. I think from there it should be clear that the question mark could get filled in with a 9. So this would be 16 minus 9 be congruent to 7 mod 11. And so we've got, therefore, the question mark can be filled in with a 9. The question mark can equal 9, and we can say that 5, going back to the original kind of equation in a sense, but congruence statement, you might say, 5 minus 9 is congruent to 7 mod 11. Alright, so let's check out another example here where now we're dealing with, instead of addition, instead of subtraction, we just did subtraction with these three, we did addition, and we did kind of a combination of things here. We're going to deal strictly with multiplication in this one with some question marks again. So we're going to say in this one we're going to find all replacements. There might be more than one. So find all replacements for the question mark that makes the statement true. And I'm going to assume the same thing as I assumed back here, that the question mark is a number less than the modular number. I'm not going to write that down again, but let's just make that assumption here that that's the case. So let's say we start off with something like this. 3 times don't know question mark is congruent to 2 mod 5. So what do I need to check? Basically what I need to check is every number here could get filled in with anything that's within the modulus system here. So this could be filled in with a 0, 1, 2, 3, or 4, anything that's from 0 to 1 less than the modulus. So let's check each one of those things here. Let's write that down first, that we're going to check each number 0 to 4 since it's in mod 5. So since in mod 5 will be my shorthand to say that. And so let's check 3 times 0 and see what that is congruent to in mod 5. 3 times 1, 3 times 2, and then I'm just going to go over here for 3 times 3 and 3 times 4. I'm not going to do 3 times 5 because 5 is not an allowed element in mod 5. So I just need to check these 5 multiplications. So what is 3 times 0? That's 0. No matter what modulus you're talking about. 3 times 1 is going to be 3 in mod 5. Now 3 times 2, this is where we have to think about it one more step here. 3 times 2 is 6, but 6 is not allowed in mod 5. 6 divided by 5 though has a remainder of 1. So 3 times 2 is 1 in modulus 5. 3 times 3 is 9. 9 divided by 5 is 1 with a remainder of 4. So that is 4 in mod 5. And then 3 times 4, that is 12. 12 divided by 5 has a remainder of 2 in mod 5. So what's the one that I wanted? Let's put this in our different color. Let's circle this. Here is the one that actually worked out. So So 3 times 4 is the same thing as 2 mod 5. Therefore, we've got our answer. The question mark in this case is equal to 4. This would get filled in with a 4 here. It would make that work out. Let's do another one similar to that, but a little bit of a twist here again. So some new twists and turns as we keep going through this. 4 times the question mark here is 2 mod 6 now. So what would make this true? So what do we need to check? We need to check each number. In this case, since it's mod 6, we're going to check the digits 0 through, or the numbers 0 through 5 now instead. So check each number 0 through 5 since we're in mod 6. And so let's put that here. We got 4 times 0, 4 times 1, 4 times 2, 4 times 3, 4 times 4, 4 times 5. What are all those congruent to in mod 6? So 4 times 0 is still 0 in mod 6. We have 0 with a remainder of 0. So that is 0 in mod 6. This will be 4 in mod 6. This would be 8, but 8 in mod 6 is 2 because you have a remainder of 2 when you divide 8 by 6. 4 times 3 is 12, which is 0, no remainder, with 12 in mod 6. If it helps you to actually write what they equal and then do the modulus from there, you're welcome to do that too. This is going to be 16. 16 divided by 6, you'd have 2 wholes with a 4 as a remainder. So this is 4 mod 6. And you've got this last one, 20, is going to be, you'll have 18, or you'll have 3, 18 times 3, not 18 times 3. 3 times 6 is 18. And so you have a remainder of 2 left over. So you notice this pattern, it kind of repeats itself. 0, 4, 2, 0, 4, 2. Which ones give you what you wanted? There's actually 2 here that give you what you want. This one, so put this in a different color, this one, and this one. Give you what you wanted. And so I would say, therefore, the question mark could equal, well, it could either be 2 or it could be 5 in this case. So 2 or 5. Remember, we're not going past the modulus, what's allowed in the modulus. So we're not going past 5 here. So the question mark is going to be 2 or 5. And so let's do one more just like that. You just continue this under your example 6. I just ran out of space there. So let's say we got 2 times the question mark is congruent to 3 in mod 4. Let's figure out what would make this true. So what numbers do we need to check? We need to check the numbers just like here. We're checking 0 through 4, 0 through 5, and mod 5 and mod 6. Now we have mod 4, so we've got to check the digits or the numbers 0 through 3. So let's check each number 0 through 3 since we're in mod 4 now. And let's see what we get. So 2 times 0. That would be congruent to, and I'll just write all the numbers in right now. 2 times 1, 2 times 2, and 2 times 3. Let's see what each one of those are congruent to. So 2 times 0, that's 0 mod 4. 2 times 1 is 2 mod 4. 2 times 2 would be 4, but in mod 4 there's no remainder with the 4. So 0 mod 4, and 2 times 3 would be 6. You'd have a remainder of 2 with that when you divide it by 4. So you look at this and you take out your different color and you're like, oh, wait a minute, it's supposed to be 3. I don't see any 3. That's right, there is no 3. So there is actually no answer. Sometimes there's not going to be a value that will actually work for the question mark. So let's write that down. So this one, there's no value that makes a statement true. So the answer is no solution. That is a possibility with a question like this. So here the answer is no solution. Alright, so let's check it out just a couple more examples. Almost there. So example 7, we're going to do the following. We're going to construct a mod 3 addition table. And show that the mathematical system is a commutative group. And we're going to, just like before in some of the problems we had, we're going to assume that the associative property holds. If we couldn't assume that, it'd be kind of it'd be quite tedious. You have a lot of work to do with that associative property to check each and every single possibility. So assume that the associative property holds. Okay, so let's start off by making our mod 3 addition table. This one I'll just use this rather than the column itself, but we're doing addition. That's my binary operation. I'm doing 0, 1, and 2. That's all I need to check in mod 3, just doing 0, 1, and 2. So what's 0 plus 0 in mod 3? That's 0. 0 plus 1 in mod 3 is 1. 0 plus 2 in mod 3 is 2. And then the same thing with 1 plus 0 and 2 plus 0 is going to be that. 1 plus 1 is 2 in mod 3. Now this is where it gets a little trickier. 1 plus 2 is 3, but 3 in mod 3 is 0. There's no remainder when you divide 3 by 3. Same thing with 2 plus 1, no remainder. 2 plus 2 is going to be 4, but 4 has a remainder of 1 when you divide it by 3. So the addition table looks like that. Pretty simple addition table there. And now we just need to check those steps from there. So remember your CIIAC from before. That's like we had here in lesson 10.2. So stuff like this. We need to check those 5 things to see if it's a commutative group. So we're going back to that, practicing that one more time. So that first C stood for closure. Put this in a different color next to that. Let's keep that consistent the way we had it before. So closure, is the system closed? Everything that's here and here, is that the only elements you see here? Yes, it is. So you would say the set is closed. Step 2, we're checking for the identity. Is there an identity element in this set? So do you have the row repeated here somewhere? Yep, it's right here. So it looks like 0. Just check the column 2. Yep, looks like 0. So the identity element is 0. Just got blended together a little too much there. Is 0. There we go. And so this was our first I. These are both good. Now we're going to check the second I. And we'll put a check mark there yet. Maybe I can, maybe I can't. So I need to check if there's an inverse for each value. So basically just need to check 3 different values. Do I have 0 plus something that's going to give me 0? Do I have 1 plus something that's going to give me 0? And do I have 2 plus something that's going to give me 0? Is there some value for each one that gives me the identity element? So 0 plus 0 gives me 0. 1 plus 2 gives me 0. And 2 plus 1 gives me 0. So there is in fact that. So I wrote that down wrong. I said it right, but it's supposed to be 1 plus 2. There we go. And so that checks out too. So I'll put a little check mark there. Now let's check step 4. We're checking the associative property. And if we had to check each one, this would be pretty tedious. We'd have to do quite a few combinations. But this, we're supposed to assume that the associative property holds. So we'll just write that down, that we're told the associative property holds. And so next to this would be my A part. I would put a check mark there. We're good to go on that. So just one more thing to check, is it commutative? And so we could check each value. We could do 0 plus 0. We could do 1 plus 0 and see if it's the same as 0 plus 1, and so on. But we don't need to do that. Remember, we can just look at our main diagonal. So let's circle this here in your different color and see if it's symmetric about that. So 0 and 0, 2 and 2, 1 and 1. There's definitely symmetry there. So we can say the table is symmetric about the main diagonal. If you said the word across, I wouldn't get too uptight or upset about that. I say across sometimes instead of about myself. So either word is fine to me there, but about is the way that the book phrases it, so we'll use that here. So is this a commutative set, or a commutative group rather? These, all 5 of these, they hold, so yes, it is. So we can say therefore it's a commutative group. And so we were assuming that it would be, because it says show that it is rather than say check if it is, but I will still box it in. So we got our answer there. So just one more example, time to make it kind of practical. This guy is a pretty famous bodybuilder. He's since retired, but Ronnie Coleman, one of the more famous bodybuilders of the more modern day era. You could think of Arnold Schwarzenegger as being one that was a little older. But let's write this down. So these bodybuilders, they work out a lot, but they also take days off too, and it's important for the body to be able to recuperate and to repair itself, repair the muscular damage done by lifting weights. So a certain bodybuilder takes a day off every 4th day, we're going to say. So hits the weights real hard those 3 days and then takes a day off the 4th day. We're going to determine the following. So let's start off with this. If today is the 52nd day of his workout regimen, is he taking the day off? So basically we think of day 0 as a day off, and then day 1 he's working out for 3 days. So day 1, 2, 3 he's working out, and then day 4 he takes a day off, and then days 5, 6, 7 he's working out, day 8 he takes a day off. We don't want to count all the way up to 52. If I change this to like his 186th day of the workout regimen, we wouldn't want to count that all up. This is where something like modular arithmetic comes in very handy. So we can do something just like this. We can just take 52, and I know that every 4th day he's taking the day off. So if I divide 52 by 4, that gives me 0, and it gives me 13 with a remainder of 0. So I know that this cycle, this pattern continues. We got workout, 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 not working out. Workout, 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 not working out. So every 4, it's like, if we take modulus 4, that 4th day is the non-workout day. So we can say, therefore, is he taking the day off? Yes, he is. Since 52 is congruent to 0 mod 4. So that every 4th day he's taking that off. Let's write this in a different color, just as a reminder of why this worked out. So we're using, or why we used mod 4. We're using mod 4 since he has every 4th day off. And then part B, last part here, if he had the day off 2 days ago, was he working out 30 days ago? Interesting question. How can we figure this out? So the way I saw this at first, there's different ways about this. If you really wanted to count, you could do that, but in terms of doing this the way we need to do this, or the way I'm requesting you to do this, we would not just be counting. We need to do this using modular arithmetic. So this could be a number like 300 days ago. We would definitely not want to count 300 days. So let's see how we could think of this. So I'm going to write out that W is the workout day and N is going to equal not a workout day, so a non-workout day, a rest day in other words. And so the cycle would continue every 4 days. We'd have a non-workout day, then a workout day, then a workout day, then a workout day, and that pattern would continue. So if this was today, let's put this in a different color now. So if this is today, this I could consider to be day 30 because we're talking 30 days ago. So in terms of figuring out this problem, I would call this day 30. This would be 2 days ago right here. And if you go back 2 days, 1, 2, you got day 28. So again, there's other ways to think this through. This is just the way I saw it first. So here you have 1 4-day workout cycle. And so we can think of it like this. We go back 4 days each time, back 4 days each time. We're going to have a non-workout day, a non-workout day. And so basically I can just divide 28 by 4. I can think of it in terms of modular arithmetic as this, since 28 is congruent to 0 mod 4. If I go back 28 days, I would have another N. I would have a non-workout day. So he was not working out. Slacker. Not working out 30 days ago. No. Your body needs rest. That's good to get some rest. Just not day after day after day after day getting rest, but every once in a while your body needs some rest. I think every 7th day there's a good reason why our weeks are 7 days long, because I think that's a good habit to have every 7th day to take a nice day off. So hopefully you found that helpful in helping you out with your classwork. Please let me know if you have questions, and if you ever see anything, just a quick reminder here, if you ever see anything that I do wrong, incorrectly, or you see a typo in here, let me know. If you are correct, I'll reward you with some bonus points, but please make sure that what you are telling me is actually incorrect. Please don't make me waste my time basically going back and checking something that was right in the first place. So just double check, make sure it's actually wrong before you would tell me that. But hopefully that helps you out, and let me know if you have any questions in class. Thanks guys.